All right, so
We're diving into some fascinating stuff today.
your deep dive request is all about Albert Einstein.
Okay.
You've handed us a treasure trove, mostly from Walter Isaacson's biography.
Einstein, his life and universe.
Right.
And it seems like you're interested in more than just Messiah, right? You
Yeah.
want to understand the man, the influences,
The person behind the theories.
and that's where it gets really interesting.
Because understanding Einstein's personal life, his quirks and passions.
Can give us amazing insights into how he revolutionized our understanding of the universe.
Exactly.
So, where better to start than childhood?
Okay.
Isaacson paints the picture of a young Einstein who was actually slow to talk.
Ah.
But he had this rebellious streak, especially when it came to authority figures like those strict school teachers.
It's almost as if that resistance to being told what to think.
Fueled his independent thinking later on.
Isaacson highlights how, even as a child, Einstein was constantly questioning.
Always curious about how the world worked. A pivotal moment was when his father gave him a compass.
This simple object sparked a lifelong fascination with unseen forces.
And it speaks to something Einstein himself said.
Imagination is more important than knowledge.
Right.
This wasn't just a throwaway line, it was at the core of his scientific approach.
Absolutely.
He wasn't content with rote memorization or accepting things at face value.
He was constantly visualizing, imagining, playing with ideas in his head.
So,
But this independent streak wasn't always appreciated.
Isaacson mentions how Einstein even sarcastically referred to some of his professors as infallible.
Which gives you a sense of his wit and his willingness to challenge dogma.
But this rebellious streak wasn't just about being a contrarian.
It was about staying true to his own curiosity, even when it meant going against the grain.
Like when he turned down a stable job at a company, much to his family's dismay, to pursue a career in science.
It's important to remember the context here.
His family's electrical business was struggling.
And they likely saw that job as a way to help out. But Einstein was driven by a pure passion for knowledge.
Even if it meant financial uncertainty, it speaks volumes about his dedication to his craft.
And this brings us to another fascinating aspect of Einstein's life.
His relationship with Mileva Maric, his first wife, a
Below.
brilliant physics student in her own right,
They met at the Zurich Polytechnic.
where, remarkably, she was the only woman in Einstein's section.
Wow.
Their shared passion for science was a powerful bond.
Isaacson really digs into the complexities of their relationship.
It was passionate, intellectual, and ultimately tumultuous.
They faced opposition from their families, societal pressures of the time.
And the tragic mystery surrounding the fate of their first child, Liesl, born before their marriage.
It's a side of Einstein we often don't hear about: the personal struggles, the heartaches.
But these experiences undoubtedly shaped his worldview, and perhaps even influenced his scientific thinking.
It's almost like a soap opera mixed with theoretical physics.
And speaking of physics, there's this detail about Einstein's time at the Bern Patent Office that always fascinates me.
You wouldn't think analyzing inventions would be a catalyst for groundbreaking scientific thought, right?
Right. It seems almost contradictory.
But Isaacson argues that this seemingly mundane job was actually instrumental in shaping Einstein's breakthrough thinking.
So how did that work?
Was he just surrounded by blueprints and light bulbs having eureka moments?
Think about it day after day. He was immersed in the practical applications of physics.
Analyzing devices like systems for synchronizing clocks using electrical signals.
This constant exposure to real-world problems, to the challenges of applying theoretical concepts to practical inventions.
Sparked his imagination.
So instead of stifling him, this boring job actually pushed him to think differently.
To question the very nature of time and space.
And that leads us, of course, to 1905, the legendary miracle year.
Einstein published 4 groundbreaking papers that would redefine physics on light quanta, Brownian motion, special relativity.
And the one equation everyone knows, E fell.
Each of these papers, on their own, was a revolution.
Take light quanta, for instance,
This built on the work of Max Planck.
who had proposed that energy was emitted in discrete packets, or quanta.
Right.
But even Planck himself was hesitant about the full implications of his own idea.
He thought maybe it was just a mathematical quirk.
Not necessarily how the universe actually worked.
Exactly.
But Einstein saw beyond the equation.
He proposed that light itself wasn't just a wave, as was the prevailing theory.
but also behave like a stream of particles, these quanta of light. We now call them photons.
And this explains something that had puzzled scientists for years, the photoelectric effect.
This is where shining light on a metal can actually knock electrons loose.
Right.
It just didn't make sense with the wave theory of light alone.
It's like throwing a beach ball at a
The
sandcastle.
waves from the ball aren't going to dislodge individual grains of sand.
But if you throw a pebble, you can knock some loose.
Einstein's insight was that light could act like those pebbles, those photons.
Carrying discrete amounts of energy that could interact with matter in this way.
And to think, this groundbreaking work stemmed from a mind that was immersed in the nuts and bolts of patents and inventions.
It really highlights the unexpected ways in which inspiration can strike.
It reminds us that breakthroughs often happen when we connect seemingly disparate ideas.
When we allow ourselves to question established norms.
And let's not forget his work on Brownian motion, which you touched upon earlier.
Right.
This might seem like a less flashy discovery than relativity.
But it was equally profound in its implications.
Right. It's easy to overlook Brownian motion.
This seemingly random jiggling of particles suspended in a fluid, think of dust motes dancing in a sunbeam.
Yeah.
But Einstein saw something deeper, something that had eluded scientists for decades.
At the time, the very existence of atoms and molecules was still debated in some scientific circles.
Einstein's analysis of Brownian motion provided crucial evidence for their reality.
He showed that those seemingly random movements were actually the result of countless collisions with even tinier, invisible particles, the atoms and molecules making up the fluid itself.
It was a brilliant piece of detective work connecting the invisible world of atoms to the visible world of macroscopic phenomena.
He was literally revealing the invisible.
And then, of course, there's special relativity.
Arguably his most famous work. Where do we even begin?
Well, it all started with a thought experiment that Einstein had as a teenager.
He imagined himself chasing after a beam of light.
Okay.
If light was a wave, like everyone believed at the time.
Wouldn't it appear stationary to someone moving alongside it at the speed of light?
That seems logical, right?
If you're keeping pace with something, it should look like it's standing still.
Exactly. But that contradicted what was known about the speed of light from Maxwell's equations.
Which showed that the speed of light in a vacuum is constant.
No matter how fast the source of light is moving.
Huh.
This discrepancy bothered Einstein for years.
He must have felt like he was missing something fundamental.
Like the universe was playing a cosmic joke on him.
And that's what's so incredible about Einstein, his ability to hold on to those seemingly contradictory thoughts.
To keep wrestling with them until he found a solution.
So what was the solution?
How did he reconcile this cosmic joke?
His groundbreaking insight was that space and time were not absolute.
As everyone had always assumed, but were relative to the observer.
Okay, hold on.
Relative to the observer. That sounds like we've stumbled into a philosophy lecture.
Break it down for me.
Imagine two people, one standing still on a platform, the other on a train speeding past.
Intuition tells us they both experience time at the same rate.
But according to special relativity, the person on the train would actually experience time slightly slower than the person on the platform.
Wait, seriously?
Time itself slows down.
It's mind-bending, right?
But it's been experimentally verified countless times. It means time isn't a universal metronome ticking away at a constant rate for everyone.
It's more fluid, more intertwined with motion than we realize.
And that leads to even weirder implications, right?
Like length contraction.
Exactly.
Objects moving at speeds close to the speed of light actually shrink in the direction of their motion.
At least from the perspective of a stationary observer. The faster they move, the more they shrink.
Okay, we've definitely gone down the rabbit hole now.
I think my brain needs a moment to catch up.
I don't blame you.
Special relativity is full of these counterintuitive concepts.
But it's these very concepts that have revolutionized our understanding of the universe.
It's almost like Einstein gave us a new way of seeing reality.
He swapped out the lenses in our cosmic glasses.
And let's not forget the most famous equation in history, E-MCA.
Which Einstein derived from his special relativity theory.
This equation elegantly shows the equivalence of mass and energy, two things we typically think of as completely separate.
It's amazing how something so simple-looking can hold such profound meaning.
So, in plain English, what does E-MCA actually mean?
It means that even a tiny amount of matter contains an unimaginable amount of energy.
This is the principle behind nuclear power.
A tiny bit of uranium can release a tremendous amount of energy when its nucleus is split.
And of course, it's also the principle behind the atomic bomb.
which is a much more somber application of this equation.
Indeed.
Einstein's work had profound and sometimes unintended consequences.
So we have these 4 groundbreaking papers published in a single year. The miracle year. Yeah. You'd think he'd be a shoo-in for a professorship, right?
You'd think so. But Einstein's journey to academia wasn't that simple,
He faced challenges.
some stemming from prejudice and professional jealousy.
It's hard to believe that someone with his genius would face roadblocks.
But the world doesn't always recognize brilliance right away, does it? Isaacson suggests that anti-Semitism played a role in the difficulties Einstein faced.
It's a sad reminder that even the greatest minds are not immune to the prejudices of their time. Einstein actually considered becoming an insurance salesman at one point because he was struggling to find a decent academic position.
An insurance salesman.
Can you imagine him going door to door trying to sell life insurance policies? Thankfully, fate had other plans.
His friend, Marcel Grossman, came to his aid again, helping him secure a position at the Zurich Polytechnic.
It might not have been the prestigious professorship he deserved,
But it provided him with a stable income.
and more importantly, the time and freedom to continue his research.
And that's when things got really interesting.
Because this is where that happiest thought of his comes in, right?
The one that would lead to his general theory of relativity.
Yes, it was a simple but profound realization.
Einstein imagined a man falling from the roof of a building.
Oh.
He realized that while the man was falling freely, he wouldn't feel his own weight.
It's like that brief moment of weightlessness you feel on a roller coaster when it plunges down a steep drop.
Exactly. Einstein's genius was to connect that feeling of weightlessness to the nature of gravity itself.
He realized that the effects of gravity are indistinguishable from the effects of acceleration.
This became known as the equivalence principle.
So, standing on Earth's surface, feeling the pull of gravity, is equivalent to being in a spaceship accelerating upwards at a constant rate.
Precisely. This seemingly simple insight was a radical departure from Newton's view of gravity as a force acting at a distance.
It would become the cornerstone of his general theory of relativity.
So this happiest thought, this equivalence principle, was just the beginning of a long and arduous journey for Einstein.
He spent nearly a decade grappling with complex mathematics, trying to develop a theory that would encompass this new understanding of gravity. Isaacson describes it as a period of intense intellectual struggle, even for someone of Einstein's genius.
Well, he was trying to rewrite the laws of physics to explain how gravity works on a cosmic scale. What were some of the biggest hurdles he faced during those 10 years?
One of the biggest challenges was finding the right mathematical language to describe his ideas. Traditional Euclidean geometry, the kind we learn in school, deals with flat surfaces. But Einstein realized that gravity wasn't about forces acting at a distance. It was about the curvature of space-time itself.
So he needed a new kind of geometry to describe this warped space-time.
Exactly. He needed non-Euclidean geometry, which deals with curved surfaces. Luckily, his old friend Marcel Grossman, who had helped him get his job at the Polytechnic, was an expert in this field.
Grossman to the rescue again. It's amazing how important those personal connections can be in shaping a scientific journey.
It really is. Grossman introduced Einstein to the work of mathematicians like Bernhard Riemann, whose work provided the tools Einstein needed to describe the warped geometry of space-time.
Okay, I'm trying to wrap my head around this. So if gravity is about the curvature of space-time, how do we visualize that?
Think of a bowling ball placed on a trampoline. The ball creates a dip in the fabric of the trampoline, right?
Right, makes the trampoline sag in the middle.
Now imagine rolling a marble across the trampoline. Instead of traveling in a straight line, the marble would follow the curve created by the bowling ball.
Ah, I see. So the bowling ball is like a massive object in space, like a star or a planet, and the marble is like a smaller object being pulled towards it by gravity.
Precisely. That's a simplified analogy for how general relativity describes gravity. Massive objects warp the fabric of space-time, and other objects, even light itself, follow the curvature of this warped space-time.
Mind-blowing. But Einstein wasn't just relying on analogies, right? He was doing some seriously heavy-duty math to back it all up.
Absolutely. He spent years developing the field equations of general relativity, which mathematically describe how matter and energy warp space-time and how that curvature dictates the motion of objects. It was a monumental effort filled with dead ends and moments of self-doubt. Isaacson even shares a quote from Einstein where he confides in a friend saying, "This problem is so damnably difficult that I sometimes despair of ever coming to a solution."
It's amazing to think that even Einstein, with his towering intellect, had moments of doubt and frustration.
It just goes to show that breakthroughs often come after periods of intense struggle and perseverance. And for Einstein, the breakthrough finally came in November 1915, when he presented his field equations to the Prussian Academy of Sciences.
And that was that general relativity was born?
Well, it still needed to be tested, of course.
Yeah.
And one of the most famous tests came in 1919 during a solar eclipse. Einstein had predicted that the gravity of the sun would bend the path of starlight passing near it, an effect that would be most noticeable during an eclipse.
So scientists could observe stars that should have been hidden behind the sun because their light was being bent around it.
Exactly. And that's exactly what Arthur Eddington, a British astronomer, observed during the 1919 eclipse. His observations confirmed Einstein's predictions and made headlines around the world, instantly catapulting Einstein to global fame.
It's not every day that a scientific theory makes someone a household name.
It was a major triumph for Einstein and a turning point for our understanding of the universe.
But even after achieving such success, Einstein didn't rest on his laurels. He continued exploring the cosmos, using general relativity to develop a model of the universe itself.
This is where his biggest blunder, as he later called it, comes into play: the cosmological constant.
Ah, yes, the cosmological constant. Tell us more about that. What was it and why was it such a blunder?
At the time, most scientists, Einstein included, believed the universe was static, that it wasn't expanding or contracting. But his equations of general relativity suggested that the universe should either be expanding or collapsing. He didn't like that idea, so he added this extra term, the cosmological constant, to his equations.
So he fudged the math a little to make the universe fit his preconceived notions. Seems a bit out of character for someone who is constantly challenging the status quo.
It's true, but remember, even geniuses can make mistakes, and even the most brilliant minds can be blinded by their own biases. In Einstein's defense, it was a reasonable assumption at the time. But when astronomical observations in the 1920s showed that the universe was in fact expanding, he realized his mistake.
And to his credit, he owned up to it. Not many people would willingly proclaim their biggest blunder to the world.
It's a testament to his humility and his commitment to scientific truth. But here's the ironic twist. The cosmological constant has made a comeback in recent decades.
Wait, really? So Einstein's blunder wasn't a blunder after all?
It's more nuanced than that. You see, in the late 1990s, astronomers discovered that the expansion of the universe isn't just happening, it's accelerating. This was totally unexpected, and it suggested that there's some unknown force pushing everything apart.
So is this where dark energy comes in, that mysterious force that makes up a huge chunk of the universe, but that we still don't fully understand?
Exactly. And to explain this accelerated expansion, scientists have resurrected the cosmological constant, repurposing it as a representation of this mysterious dark energy.
So even Einstein's mistakes can lead to new discoveries and deepen our understanding of the universe. It makes you wonder what else he might have gotten right that we haven't fully grasped yet.
It's a humbling thought, isn't it? But even as Einstein was grappling with the vastness of the cosmos, he was also wrestling with the inner workings of the atom. He had helped to launch the quantum revolution with his work on light quanta and the photoelectric effect. But he had deep reservations about some of the implications of quantum theory.
Right. He famously said, God does not play dice with the universe, expressing his discomfort with the probabilistic nature of quantum mechanics. It seemed to clash with his deeply held belief in a universe governed by order and causality.
It did. And this tension between Einstein's deterministic worldview and the probabilistic nature of quantum mechanics became a major theme in the latter part of his career. He spent decades searching for a unified field theory, a single framework that could elegantly explain both gravity and electromagnetism, the two fundamental forces known at the time.
So he was trying to find a grand unified theory of everything, a theory to rule them all.
Exactly. He wanted to find the underlying order, the hidden connections between seemingly disparate phenomena. And while he didn't succeed in finding a unified field theory before his death in 1955, his quest continues to inspire physicists today.
It's amazing to think that his work done nearly a century ago is still driving scientific inquiry today.
It is, and it speaks to the enduring power of Einstein's legacy. He wasn't just a brilliant scientist, he was a revolutionary thinker who taught us to question our assumptions, to embrace curiosity, and to never stop searching for deeper truths about the universe and our place within it.
Well said. I think we've covered a lot of ground in this deep dive. From Einstein's childhood fascination with the compass to his groundbreaking work on relativity and his quest for a unified field theory, we've seen how his personal experiences and his relentless curiosity shaped his scientific journey.
We've seen how his willingness to challenge dogma, to embrace the unknown and to think differently allowed him to unlock some of the universe's greatest secrets.
It's been an incredible journey through the life and mind of a true visionary. And on that note, thanks for joining us for this deep dive into the world of Albert Einstein. We hope you've gained some new insights and perhaps even a renewed sense of wonder about the universe we inhabit.